Okay, hello and welcome back to Chemistry Talk. Today I'll be continuing kinetics and we'll be discussing reaction order um, and continuing with writing rate laws. Now, if you recall, reaction order can be defined as the power dependence of the rate of the concentration of the reactants. So your standard rate law would equal or would be the rate, so the rate at which you're forming the products, and that would equal K, which is a rate constant that's different for every reaction. It would also equal K times the concentration of your first reactant with order with respect to that reactant, and the concentration of your second reactant with order with respect to that reactant. So the overall order of a reaction can be determined from the rate law. So in this case, since we're just using all letters, the overall order would be the sum of the exponents, m plus n. In other words, the order of the reaction is dependent on the power of the concentrations of the reactants, so that would be m and n. If you're given a certain data table for a reaction and you want to determine the order, the rate law, the rate constant of that reaction, you just have to manipulate the data points to find the order and then kind of work backwards. So I'll show you how to do that here. Here I'm giving you the formation of nitrogen gas and gaseous water by reducing nitric oxide with hydrogen. So I've given you a data table here. I've given you the initial concentrations in molar of the nitric oxide and hydrogen gas. I've also given you the rate at which those concentrations form products. In this case, it's the gaseous water. So I ask you 5 things. What's the order with respect to nitric oxide? The order with respect to hydrogen gas? The overall order? What is the rate constant? And then we're going to write the rate law. We cannot write the rate law without determining everything above. So this is the last thing you're going to want to do. First, I'm going to start off by determining the order with respect to nitric oxide. How you do this is you manipulate your data table here. If you see, I have 3 rows of data here. I have 1 row, 2 row, 3 rows. Going across horizontally, in my first row, I have the same amount or the same concentrations of reactants, and I form the gaseous water at this rate. In the second line of data, I've doubled the concentration of hydrogen gas, kept the concentration of nitric oxide the same, and the reaction occurs at this rate. The third line of data is the opposite. I've doubled the nitric oxide concentration, lowered the hydrogen gas concentration, and the rate occurs here. So when you're looking at the order with respect to nitric oxide or to hydrogen gas, you're not going to want to use the data points where the concentrations are equal, because that's just going to give you 1, and that's not accurate. So you want to use the data where the numbers are different for the initial concentrations. So I'm going to be using this line because that's where it's different, but it does matter whether I use the first or second line of data to determine the order here, because I need to look at the concentration of nitric oxide when the hydrogen gas is the same, or else I would be manipulating 2 lines of data, and then that wouldn't work. So I'm going to use this line of data for the order of NO, but I need to use the first line of data as well. I cannot use the second line because if you see here, the hydrogen gas concentration is changing from here to here, and that's not going to work. The hydrogen gas needs to stay the same, so we can just look at the nitric oxide. So don't make that mistake. So order with respect to nitric oxide. So the first thing I'm going to want to do is find the jump in my concentration. So I'm going to take the 0.2 and divide it by 0.1. just taking the bigger number over the smaller number, not the opposite, or else you'll get fractions. And I get 2. So what I want to determine is 2 to what power will give me my change in formation. And the change in formation is the same thing. It's the bigger over the smaller. So it would be 4.92 times 10 to the negative third over the 1.23 times 10 to the negative third. And that should give you 4. Just double check that, but that should give you 4. Type that in here. Yes, so you get 4. So 2 to what power will give you 4? Well, 2 to the second power would give you 4, which means that the order with respect to NO is 2. So the order with NO is 2, because 2 to the second power would give you 4. So you're looking at the power, so the order with respect to NO is 2. So I'm going to write 2 here. Erase this now. So now we're going to do the same exact thing for the hydrogen gas. So looking at the hydrogen gas, I want to use the data where the hydrogen gas is changing. So I'm going to need to use this line of data. But am I going to use the first or second as well? Well, I'm going to need to use the first here because I need to look at it where the concentration of nitric oxide is not changing, and that would be here. If I used this last line of data with the second, it wouldn't be accurate because we're changing both concentrations and it just would get weird and confusing. So you don't want to do that because you're going to get the wrong number. So first I'm going to look at order with respect to hydrogen gas. So same thing here. I'm going to take the 0.2 over the 0.1, and once again I get 2. But the rate is different, so I need to see how the rate's going to change. So I'm going to take that 2.46 times 10 to the negative third over 1.23 times 10 to the negative third, and I'm going to do that division. That way, I'm doing the same thing like I did with the nitric oxide. I'm determining the order with respect to hydrogen. So when I do that division, I get 2. Okay, well 2 to what power is going to give me 2? 2 to the first power will give me 2. So the order with respect to hydrogen gas is 1. So that is the bulk of the math here. Now we're just going to use what we just found to answer the remaining questions. Important to note here that if you mess up on this initial part, your answers for the next parts are going to be wrong. So just be careful. Okay, I'm going to go back to red now. What is the overall order of the reaction? Well, the overall order would be the sum of the order. So it would be 2 plus 1. So the overall order here is 3. It's the sum of these two numbers. What is the rate constant for the reaction? Okay, first I'm going to write the rate law. Now, this isn't going to be the final rate law. It's just going to be what we know right now, because I don't know what K is. So K is still going to be a variable. But I do know the order with respect to our reactants. So the order with respect to nitric oxide is 2. And the order with respect to hydrogen gas is 1. So what can I do here to find K? Well, I can just use a line of data, plug in what I know, and just solve for k. So let's do that. It doesn't matter what line of data I choose. You should get the same number. So I'll use gray here. So what is the rate? So I'm going to use, let's use the second line of data right here. That's not a good color. Let's use the second line of data. So my rate, 2.46 times 10 to the negative third, and like I said, you can choose whichever line you want, doesn't matter. 2.46 times 10 to the negative third equals that K times the concentration of nitric oxide. Okay, well in this line, it's 0.10, and that's raised to the second power, and the concentration of hydrogen gas, which is 0.2 here, and that is raised to the first power because it's order with respect to hydrogen, and that's 1. So here I'm just going to solve for K. So when I do that, I'm going to take 0.1 and square it, times that by 0.2, then take the rate, 2.46 times 10 to the negative third, and divide it by that number, which is 0.002. So I get K for this reaction to be 1.23, and this is in inverse seconds. So K equals 1.23. So finally, what is the rate law for this reaction? Well, we know everything now. The rate, and this could be a lot of different rates, so you don't write the rate would equal K times the concentration of NO raised to the second power, because its order with respect to NO is 2, and the concentration of hydrogen gas, which is 1. Order is 1. Now we could put in our number for K here. We could say that the rate would equal, any rate would equal the K, 1.23, times the concentration of nitrogen gas squared, because its order is 2, times the concentration of hydrogen gas, and that order is 1, so it would just be 1. So what does this mean? This means that I can determine the rate of this reaction at any concentration of NO or hydrogen gas by using this rate constant. It's a rate constant. It doesn't change. It stays the same for the reaction. This reaction will always have that rate constant. Now, I could give you different concentrations of nitric oxide and hydrogen gas, and you can find the rate just by having this rate constant and by knowing the order. I hope this helped you to understand how to determine order of reactions and the rate constant and writing the rate law. In future videos, we'll be doing more math problems involving kinetics with first order and second order reactions using the integrated rate law equation.